Hello and welcome. In this video I'll be showing you how to do a hypothesis test. Starting off with a binomial, we have our binomial here with our end value, number of trials being 50, number of probability of success of the trials being 0.5. Setting up a hypothesis test for this would give a null hypothesis as p being equal to 0.5 and our alternate hypothesis being p, one of three options: p is greater than 0.5, p is less than 0.5, or p is not equal to 0.5. Right? Now, these three options are a little bit hard to understand if you don't understand what the graph for this function, probability function, would look like. Right? Let's say we have a probability function. That's the probability, like I've said, 0.5 here. It would go all the way up to 1, obviously. Then we have our number of trials, 50 here, coming from x equals 0 to x equals 50. Right, when x equals 0, let's say you'd have maybe one success, sorry, 0 successes, and then if x equals 50, you'd have 50 successes, just like that. The probability of doing that is going to be that function, and if we draw a graph for it, it would look something like this, should do. And it'll be like a little shape, a bell shape kind of thing. And when we look at it, we see there's bits here where there's not much, there's a very low probability, and there's a bit here where there's very low probability, which makes sense. And there's a bit in the middle where you have the highest probability. Because if you have, let's just say, probability of 0.5, 50 trials, you'd expect about 25, which makes sense, about in the middle. And it's probably the same, it's pretty much the same for all graphs. It's very similar, where you have a bit at the end, which is has a very low probability, have a bit at both ends, has a low probability, and you have a bit in the middle, which has a really high probability. And with our hypothesis test, we're trying to figure out a little thing, and this thing is to do with the significance level. Let's say I assign a significance level of 5%. It's like a leniency that you give, I guess, to your probability, because the whole point of it is saying, is our probability 0.5 or is it something else? Now, our significance level is basically saying, okay, maybe there might be a little bit of deviance from 0.5, but if it's within a certain amount, then it's fine, which is what this is saying. But in a visual way, if we look at this significance level, then it will be, let's say for 5% significance level, let's draw this on. If it's greater than 0.5, you'd expect more. So you'd go to this side, the upper tail, I'll shade in red up here, and there'd be like a shaded area here where the sum of all the probabilities would be, let's say, because it's 5%, the sum of all the probabilities would have to be 0.05, right? 5%, all the probabilities here. Now, if it was less than 0.5, it would be the same, just on this side here. I'm shading it in red, which would also be probability of the sum of these would be 0.05. And let's say we have, I don't know, not equal to, then that would mean that it would be both tails. So it will be both of them. Instead of, because it's 5% significance level, that 5% will be split between these two. So each of them would, in a two-tail test, would have, the sum of the probabilities would be equal to, or at least as close as to 0.025. In other words, 2.5%, so half of this will be split between both of these tails. But yeah, I'm going to go over a few examples of this, and and hopefully this section made sense. But yeah. So in this first question we have someone who's playing the game. He's playing the game 32 times, and he's winning it 1/3 of the time, supposedly, and he's in the trial that we've done, he's won it 16 times, and we're trying to figure out whether that shows that his new method for playing the game is actually increasing his probability of winning it. Now, we go to this binomial here, so we've got our number of trials 32, probability 1/3, and our null hypothesis where the probability is staying the same, 1/3, and our alternate is where it's increasing because of the new method. Coming onto this diagram here, I've shown the probability diagram graph, and this is showing us the upper tail, I suppose, of this test. You've got a lower tail here, you've got an upper tail here. Our test is going to be of the upper tail, because obviously greater than 1/3, so it has to be an upper tail test. And as you can see here, what we'll do is we'll just get the probability of 16, add it to the probability of 17 for the binomials, probability of x being 16 plus 17, all the way up to 32, and that sum, so the sum of probabilities, the sum of p, is related to your significance level, as I've said, 5%. Now, the significance level is basically saying, right, you've got your data, you've got the main bit of data here, which is like the most highest probability data, and then you've got your tails data, the tails at the very ends of the data, right? The 5% is saying to you that if your data is within 5 to 95%, right, if the probabilities are between 5% and 95%, we can say that that data is alright. We can say that H0, the null hypothesis, is true. We can say the probability is equal to 1/3. But if it's between 0 to 5, or in our case, if it's because it's an upper tail test, we can ignore the 0 to 5. We can say if it's between 95 and 100%, then we can say that the probability has actually increased, right? It's in the upper tail. The upper tail will be in that final 5%. That's what this significance level is actually telling us. So, using that information, we can say if the sum of probabilities is less than 0.05, if it's less than the significance level, in other words, if it's in that zone, the 95 to 100% zone bit, we can say that our answer will be rejecting the null hypothesis. And the opposite, of course, if it's greater than 0.05. That's going to be a little bit hard to understand sometimes. You just got to think about it as, obviously it's 95%, but we're going to be doing 1 minus that to get the 5%, I guess, because it's in the upper 5. But you might be thinking, oh well, if the sum of probabilities won't actually be 95 because we're only looking in this area. If we go from 0 all the way to 16, that would be 95, but this bit here, this red bit here, will just be 5. Right, and I'll actually come on to that now, because if we want to write that in terms of the binomial, what we'll actually do is we'll write the probability of the x value being greater than or equal to 16, because 16 is the number of successes that we said we're trying to figure out this area. Some calculators can do this straight off the bat, but if some others can't, so what you'll have to do is you'll have to write this as 1 minus the probability of x being greater than or equal to 15. That's what I was mentioning before, going from 0 to 15. 15 isn't labelled here, but it's 15. Going from that, and then doing 1 minus that, so minusing that answer and finding this red region. In my calculator, what I got was, when I did this, I just got 1 minus 0.96 234, and then that would equal 0.03766 approximately. And as you can clearly see, your 0.03766, in other words 3.7%, is less than 0.05, in other words 5%, and this means that we'll be rejecting H0, as I've said up here. In other words, our data is in the upper 5%, and that means that it's too different from everything else, so it has to be rejected. And obviously in this case, I can actually write this down. If it's greater than, then we accept. And at the end, we'll want to write a bit of context. Because we're rejecting it, that means that the method has increased the P of success. I'm just going to say P of success at the game. Right. Yeah, let's move on to the next example. So in this next example here, we have our binomial distribution here with our 75 and 0.14. 75 being the sample size, sample number of beads, 0.14 being the probability of selecting the red bead. Now we have our question here, so I'll read through it really quickly. After two children have taken the beads from the sack, the teacher decides to test whether or not the proportion of red beads has changed. So that's what the hypothesis is testing. It's testing if the proportion of beads has changed. Now, if you look at different questions that we've done, you'll see that, like for example, in this one, it's saying that you want to see like if the probability of success has increased. But in this case, trying to see if the probability of success has changed. It's a big difference, right? So instead of saying, you know, P is greater than 0.14 or P is less than 0.14, we'll be saying P is not equal to 0.14. Right? And what that actually means is that we're looking in both tails. So in this diagram here, the probability diagram, we have this lower tail, we have a lower tail and we have an upper tail, lower tail, upper tail, and because it's, because it's not equal to, it can either be less than it can either be less than, in our case we have, it can either be less than 0.14, or it can either be greater than 0.14, and in both cases, because we have a 5% significance level, we'll be splitting that, like shown here, we'll be splitting that between both tails. So what that would look like, in your calculation, we do the same as we did last time. We just used our number here, our observed value, which is 4, and use that in our binomial to get a value. So we'd say for the lower tail, we'd say the probability of x being less than or equal to 4. And when we do this, we get around about, we get 0.05. Actually, I'll be a bit more accurate. I'll say 0.01506. Now, this is 1.5% and clearly, less than the significance level. And remember, like I said before, it's a 5% significance level, but this significance level is split between both of these tails. So the actual significance for this would be 0.025. In other words, 2.5% would be half of it, because it will be split evenly between both tails. Now we've got the other upper tail, which will be, you can already tell that the upper tail won't be of use, but I'll do it anyway. But yeah. So this would be greater than or equal to 4, and you can already tell if less than or equal to 4 is this tiny number, then this would be 1 minus the probability of x being less than or equal to 3. This would also be a very, very large number, and this actually turns out to be 0.996, I believe. So this is quite a big number, obviously a lot bigger than 0.025. But in some questions, you'll have to look into both tails and see which one is, well, if any of them are actually able to be less than or in the critical region, as we call it. So if it's less than 0.025, and if it's not, obviously you would keep h0. But in our example, our number is less than our significance level. It's 0.015%, and we'd be rejecting h0 like we would do before. So I'd write it here. I'll say, so therefore we reject h0, and giving a bit of context, we'll say that the proportion of beads has decreased, so it's changed. I guess I could also mention that it has kind of decreased as well, because of course it's in the lower tail. But yeah, hope this video has been helpful, and thank you for watching till the end. Have a good day.